Newton's gravitational law, electrostatics. Yeah, I think that was it.
Okay.
Mhm.
And did you have multiple choice?
Yes, we did.
How many questions?
It was 8 questions.
I'm sure you got all of them.
I don't know.
Oh, but you got most of them.
Yes, I'd like to
Uh,
think so.
okay. No, that's good. And some of the multiple choice questions we had, did they come?
Yeah, there was one that came. I forgot
No,
which one
only
was it.
only one.
Yeah, there was one that came out in the paper.
Sure. Okay. Okay. And Newton's law, which question came? Which type of question came?
Uh, they basically asked us, okay, with Newton's, they asked us to state Newton's second law, and then we had to calculate the acceleration. So it was a pulley system. We had to calculate the acceleration, and then after getting our acceleration, we had to calculate the distance or something like that. But we had to apply what?
Grade 10.
Yeah, we had to apply grade 10 mark. Laws of
Okay.
motion.
Laws of motion. Okay.
Mhm.
Yeah, I think it's something we have done. I think we did it almost twice, if I'm not
Yes.
mistaken. Okay. And let's see. And with electrostatics, was it something hectic?
No. You remember the question that we did where uh we had to find the resultant of the 3 charges?
Yes.
Yeah, something similar came up.
Was it a linear problem
No,
or
it was not a linear problem.
oh okay, they were in a triangular form.
Yes.
But has your teacher done such a problem in class before?
I don't know. I don't remember him doing it.
Oh, because it means you were lucky for attending that last session with me.
Yes.
Because trust me, the majority of people in class wouldn't get that problem.
Mm-hmm.
They were gonna apply the same thing you were applying.
Oh yeah, I remember the
Yes. Agree you applied exactly the way I taught you. The one of using
yes,
Pythagoras.
yes, I did.
Yeah, that's why yes. And the other students, did they find the same level of difficulty as you?
Mm, no, not really. I think because we did everybody practiced past papers on their own, they had already anticipated that such a question would come up in the
Would
test.
come.
And most of
Oh,
them go to tutoring classes, so I think they probably did it in.
oh yes.
Mhm.
Yeah, yeah. Okay, that's good. Um, I want us to continue with electricity. So
Yes.
before we continue, I just want to ask quick questions. What is current?
Current is the rate of flow, no, the flow of charge, the rate of flow of charge, something like that. I don't know. In a
Yeah, you
system.
can say. Yeah, you can say. Yeah, the flow of charge. What in a system?
Not in a system.
Okay. You know what?
In a yours, I don't know.
Inside the conductor.
Oh, inside the conductor. Yes.
Yes. Okay. What is the resistance?
Uh resistance.
Mm-hmm.
I don't know, but I know that it opposes current
Yeah,
in
that's it. You are actually You're actually 100% right.
Oh,
Yeah, it's the opposition. That's it. The opposition of current. You're done. Inside the conductor. That's it. What is the potential difference across a
um,
resistor?
potential difference.
Yes.
The work done. Yeah, I don't know.
Okay, what is the formula of calculating the potential difference then? I think that will help you define it better.
It's V is equals to W over Q.
Yeah, then you have the definition already.
Mm-hmm.
So it is the work done to move the charges, pair charges.
Okay.
W, yes, divided means pair.
Yes.
Okay. What is what's the other term? Okay. What is the lost voltage?
The lost voltage.
In a second.
Lost voltage.
Yes.
I don't remember doing that.
Okay. Lost voltage is the voltage lost inside the battery due to heating or any other form of energy dissipation.
Okay. Oh, okay.
Oh, okay. What is an EMF?
EMF is the work done per unit charge by the battery.
Okay. Yeah, it could mean that, but it's the voltage across the battery when the circuit is open.
Okay.
Yes. So the EMF of the battery is the maximum power or the maximum voltage that the battery can give. It is just that when you start closing your circuit, the so-called uh, internal resistance, have you heard of that term before?
Yes.
The internal resistance of the battery reduces the EMF as soon as you close the circuit.
Mm-hmm.
And as a result, you eventually have the so-called the lost volts.
Okay.
Do you remember that the EMF is equals to the potential difference across the battery when it is closed plus the lost volts. Inside the battery, there is resistance and it's called internal resistance. Okay, so what is internal resistance?
The resistance that is inside the battery.
Exactly. Okay, perfect. Um, this will be V plus, this is the symbol of lost volts. I think it's like this. Okay. I think it's a small letter, if I'm not mistaken. Lost volts. Okay, perfect. Lost volts. Okay, so what is the formula of calculating voltage in Ohm's law? The Ohm's law formula of calculating voltage.
Uh, V is equals to I times R.
Perfect. Then, do you agree that the same value of I is the one that is going to flow inside the battery?
Mm-hmm.
And then this is the internal resistance. The symbol of the internal resistance is the small letter R. So if you take the common factor, you will have.
If I take out the common factor,
Yeah.
I'll have R plus R.
Yes. Have you seen this formula before?
No, it's a new one.
Okay. I actually did introduce it last week, but okay. The total EMF is given by the total current times the total resistance of the circuit plus the internal resistance. So the big letter R is the total resistance of the circuit, excluding the internal resistance.
Mm-hmm.
And the small letter R is the internal resistance. Okay, perfect. We have a new term in the game. It's called okay, what are the units of work done? What is the units of work done?
Work done.
Yes.
V?
Work done or work.
Is it not volts?
Work is measured in joules.
Oh,
You remember?
yes.
Okay. We have two terms that I want to introduce. Ohmic and non-ohmic resistors. Have you ever heard of these two terms? Mamsan, an ohmic
No.
resistor. Okay, an ohmic resistor is a resistor that obeys Ohm's law. A non-ohmic resistor does not. Okay. An example of an ohmic resistor, would you guess?
A resistor that obeys Ohm's law.
Yeah.
No, sir.
Okay, so the conductor or the nichrome wire, you can see a conductor. Conductor is an example.
Okay.
Nichrome wire, an example. An example of a non-ohmic resistor. It is a light bulb. Let me ask you this question. Okay, can you please define Ohm's law?
Ohm's law.
Yes.
The potential difference across a conductor is directly proportional to the current in the conductor at
Okay.
constant temperature.
At constant temperature. Okay, the question is what happens to the resistor, to the resistance of a resistor if the temperature increases?
What happens to the resistance of the resistor?
Yes.
If the temperature increases?
Yes.
Does the resistance not decrease?
The resistance?
Does it not decrease?
Okay. If you go to the stadium,
Yes.
and there's an opening, right?
Yes.
And everyone is using that opening. Ne?
Yes.
If people start to move around a lot or on some sort of a commotion, will it be hard for you to go out or will it be easy?
It will be hard.
Okay, what is the definition of resistance?
Resistance is the opposition of current.
Okay, will the resistance increase? Will the opposition of you going out increase?
Yes, it's going to be harder for me to go out.
Therefore, the resistance increases when the temperature, because when the temperature increases,
yes,
it gives the molecules energy to vibrate more, or to move around more. I don't know if you agree with that.
Yes, I agree with that.
Therefore, it becomes hard for the charges to flow because they are too excited. So the conclusion is the higher the temperature, the higher the resistance. Okay. So this is how the voltage versus I graph looks like of a non-ohmic resistor. Okay. Do you agree that, okay, what is the slope of a voltage a current graph? The slope of this graph, what does it represent? The slope is given by the change in y, which is, what is our y? V. You agree? Mamsan, are you still there? Are you still there? Mamsan, are you still there? Yeah, because I can't hear you properly now. Is it? Okay. Can you relocate to a good environment, or you can rejoin? Okay. Okay.
So can you hear me now?
Yes. Okay. I was asking what. Okay. The slope of the graph is given by change in.
V over change in I.
Exactly. Okay. So given that we have change in V over I, what rings the bell?
Resistance.
Exactly. This is a resistance. So the slope of this graph is the resistance.
Yes.
Okay, so the resistance here, you agree that is smaller than the resistance there?
Yes, yes, I agree.
Yes, as temperature increases.
Resistance also increases.
Yes, yes. Okay, so the graph here, will it be a parabola? Will it be a straight line? Will it, what type of a graph are we going to be dealing with if we have V over I?
What kind of graph is it gonna be?
Yeah.
It's not gonna be a straight line.
It will be a straight line because the resistance is going to be constant. It's going to be constant. So this is an ohmic resistor and this is a non-ohmic resistor. Okay, fine. I'm introducing new terms. I don't know if your teacher has already introduced them in class.
No, we haven't started on electric circuits.
At all.
Yeah.
You okay?
We're closing on Friday. So
Oh, and then they want to start it when you open.
yes.
Okay, no problem. No problem. So I wanted to introduce these two terms. No, just one term. Yes, one term called power. Now, power, it is, or do you want to guess?
No.
Okay. Power is the rate of work done. If you have a lot of power, you will do a lot of work. The rate of work done. So if it is the rate of work done, what will be the formula?
Rate work. Work is measured in joules, therefore it's W. And then rate, isn't it going to be W over delta T? Change in time?
Yes. Rate is always change in time, pair change in time. That's perfect. So this is power basically. And then, okay, this is the formula for power. And I want to replace W and T. I want to introduce your volts and the currents. Do you agree that V equals W over what? Over Q. You agree, right?
Yes, I agree.
Okay, so do you agree that power is given by, if I make W the subject of the formula, I will have V times Q. Do you agree with that?
Yes, I agree with that.
So this will be V Q over change in T. Okay. What is current?
The definition of current.
Yes.
Current is the flow of charge.
Is that the definition?
No. No, the rate of flow of charge.
Okay. And then the formula, is it correct?
Yeah, I think so.
Okay.
Yeah.
Okay. Can I replace Q over T? Like that?
Yes. Yeah. Oh, yeah.
Yes. Okay, now I want to introduce resistance. Ne? And I know that according to Ohm's law, I equals V over R. This is true, right? Okay. So if I replace I, I will have V times V over R, which is equals to, let me see, V squared over R. That's another formula for power. The ones that I've placed in brackets are the ones that you must bear in mind.
Mm.
Okay. So if I want to replace voltage, I want to replace voltage because here I replaced I instead of voltage. If I replace voltage, you know that V equals IR, right? You agree?
Yes.
So if I replace V by IR, what am I gonna have? I will have P equals
Uh,
I times R. I'm using this equation, by the way. I'm replacing
okay.
V, and I'll be left with I. And this will be, you agree?
Mm.
So I have four formulas of power. You can use them interchangeably. You can use them interchangeably. So I think we are done with all the terminologies in electricity. So I'm gonna try to do an example. I see Ronewa has joined. Yeah, welcome to the class, Ronewa. Okay, I just want to charge my computer quickly. It's fine. Okay, so those are the four formulas of power. Ronewa, have you started with electricity at school?
So we just ended with electrostatics. So
Electrostatics. Okay.
yeah.
Okay, yeah, we haven't done much. So I've only introduced the formulas for power. Power is given by the rate of work done, and it's given by W divided by change in time. So I replaced W by um, VQ, and we got power equals VI. So that's the second formula. The third formula, power equals V squared over R. And the fourth formula, power equals I squared over R. All of these formulas, I think you will get them from your from the table of formulas. Do you have them close by? Mamsan, do you have the table of formulas? Ronewa, do you have them? Mamsan. Hello. Are you still there? Yes. Are you having the same problem? Yeah, and then join. Oh. Ronel, can you
Yes,
hear me?
sir. Yes,
Yes.
sir, I can hear you now.
Okay, can you see the screen?
Yes, I can see the screen.
Okay, so earlier on we have, okay, can you define Ohm's law for us? Ohm's law. Ronel. Okay. Ronel, what is Ohm's law? Okay, so these are all the formulas for power. So I'm gonna get some few examples and see where we are. Okay. Mamson, can you hear me? Can you hear me?
Sir?
Can you hear me?
Yes.
Okay. So I'm trying to get few examples on electricity. Okay. Yeah, I finally got it. Okay. Let me take a screenshot. Okay. Okay. Can you see what's on the screen, Ronel? Mamswani, can you see?
Yes, sir.
Okay. I've left a piece of equation. Before we move on, Mamswani, what is the definition of power?
Sir, please repeat your question.
What is the definition of power?
The rate at which work is done or energy is transferred.
Yeah, that's correct. And what is the first formula for power? Or just name two formulas for power?
P is equal to W over change in time.
Yes.
And the second one is, wait. Oh, the second one is P is equal to VI.
Oh, yes. And the other one?
Then the third one is P is equals to V squared over R.
Yeah, okay, we can stay there. If we can stay, that's enough. Okay. The battery in the circuit diagram below has a negligible internal resistance. The resistance of a resistor R is unknown. When the switch is closed, the voltmeter reads 15 volts and the ammeter A1 reads A1 A. Okay. They say calculate the current in ammeter A. How do we go about it? Ma'am Swan, what are the steps of solving circuits? The first step, Ma'am Swan.
The first step of solving circuits.
Yes.
I don't know.
Resolve parallel resistance into effective resistor. Resistors. You know what an effective resistor is, mostly? Or the
Yes.
effective resistance. Okay, perfect. The second step is to reconstruct circuit with series connection only. Then the third step is to use Ohm's law. To get V total, I total, and R total. In other words, you're getting all the totals. Perfect. Those are the only steps that you're going to be applying, and that's it. Okay. What is the current? How can we calculate the current at A? For the ammeter reading at A?
So can we not use I is equals to V over R?
Okay. I equals V over R. Let me see which question is that. Okay. That's 4.2.1. Okay. 4.2.1. I equals V over R. And then what would be the value of V?
15.
15. The value of R?
I have a question.
Yes.
When we are using Ohm's law,
Yes.
does it always have to be the totals of the entire circuit? Like for instance,
It depends on the position that you are calculating a particular parameter.
okay.
Yes.
So can I just use 12 then as my R?
12 as your R.
Yeah.
Rhonda, what do you agree?
So I would assume so.
Okay. So both of you are saying that if I calculate the potential difference between these 2 points, I will get 15. Are you guys insinuating that?
Yes.
Rhonda, what do you also agree?
So when you ask me these questions, you make me unsure. But
You have to be
yes.
unsure. Okay. I disagree. Because that 15 volts, that is the maximum amount of voltage that the battery will give, and that 15 volts will be divided into all the resistors. The other portion will go into this unknown resistor, and then the other portion will go into the equivalent resistance of this parallel connection. And the thing is, we don't know how much voltage will be divided into this parallel setup. Do you agree?
Yes.
Okay, so because of
So
that,
can you please repeat what you just said?
okay, what I'm saying is, let's say inside the house, there is a main power supply, and I have already indicated that resistors are like appliances inside the house. So the total supply, which is the total voltage provided by the battery, is going to be divided into all the appliances. It will go into R. Some of it will go into R. We don't know how much because it's unknown. And some of it will go into this parallel connection. Are we all following?
Yes.
Okay. Therefore, nobody knows how much voltage will be across these 2 points because we don't know how much the voltage will be distributed into this um, into this parallel connection, but we need to calculate it at the end of the day. Okay, so they've already given us the hints. The reason why they've given us an unknown resistor, they know that we were going to do the mistake that we were trying to do of trying to use that 15 volts. And given that we have an unknown resistor, we can't. Let us focus on the parallel connection. Mamswan.
Yes, sir.
Okay, let me put 4 points. Point 1, 2, 3, 4. True or false? True or false? Voltage across 1 and 2 is equals to voltage across 3 and 4.
True.
True.
Mm-hmm.
Romeo, do you agree?
Sir, yes, I agree.
Okay. Mom Swan, what is the voltage across point 1 and 2?
What is the voltage across point 1 and 2?
Yes.
Are you talking in terms of calculations or
In terms of calculation.
So, I don't know.
Romeo?
Sir, I also don't know.
Okay. Do you agree that there's a flow of charge of 1 ampere flowing inside the 12 ohm resistor? Do you agree? Mom Swan?
Yes, I agree.
Okay. According to Ohm's law, we have 3 parameters, which is voltage, current, and resistance. Already we have 2 parameters. We have resistance, we have current. So what rings a bell, Mom Swan?
We can try find the voltage by using, yeah.
Okay, so the voltage across the 12 ohm resistor is given by the formula
IR.
IR. Okay, and the value of I will be
1 ampere.
okay 1, and then the resistance
The resistance, is it not 12?
it is
Please.
12.
Okay.
So this is 12 volts. So given that we have solved for the voltage across point 1 and 2, what else can we do, Mom Swan? Because we are trying to calculate the current at ammeter A.
Given that I have calculated the voltage,
Yes, across point 1 and 2.
corresponding, there would be no need for me to calculate the resistance, right? Because it's given.
Yes, we just have to leave the resistance alone. That's why they asked us to calculate it at question 4.2.2. So we just leave it there.
Okay. Then I would say I is equals to the V that we just calculated
Yes.
over the 12 ohm resistor.
Okay. And you said I is given by V over R, right? Which you said the voltage will be?
Will be 12 volts.
12
So, but
volts. Over the resistance?
resistance is also 12. We're looking for the
You're actually going
current of
backwards.
A.
We're looking for A, big letter A.
Is
Yeah.
okay.
We have already calculated A1. Oh, no. K1 was given, sorry. Yes, A1 was given.
Okay. We calculated the voltage for point 1 and 2, right?
Yes.
Okay. So I don't know how to go about this question.
Ronne, what, do you have an idea?
So would it help if we, well, I don't know if it's gonna be the same, but would it help if we calculated the voltage for 3 and 4?
Okay. How are we going to calculate it?
So we can use that formula V is equals to I times R.
Okay. V. I'm glad that this question is it's a bit tough. So V equals I times R. And what will be the value of I? Between 0.3 and 4, what will be the value of I? Okay, these people want you guys to apply the principle of parallel connection. That's why I asked you guys, what is the voltage across these 2 points? And you guys said the voltage across point 1 and 2 is equals to the voltage across 3 and 4. So do we have the voltage across 1 and 2, Mamswan?
Yes.
So if we have it, why don't we take it and use it across 3 and 4? Why can't we do that?
Okay.
Does it make sense now?
It's a bit.
Ronel, are you still confused?
No, sir.
Okay.
So
So
we're doing all
yes,
of this for 3 marks.
yes. Yes. Okay. So if you take the voltage across point 1 and 2, you will have voltage across 3 and 4. So what rings a bell now? Ronel.
So my bell is not ringing, so
Mamswani.
Um, the voltage across 0.3 and 4 is also 12 volts.
Yes.
Mm.
And then
So
use
and
that
then
information.
use it. Let me
Yes.
see. Um. Okay, if that and that is the same. Sir, wait. The
Yes.
resistance for 0.3 and 4, right?
Yes.
Don't they also give you 12?
Yes, it will be 12 volts. Oh no, you mean the resistance?
Yes.
The resistance will be 12, yes.
Okay. So because, but where would I apply 12 volts? Okay, so you would say I is equals to
Okay.
V over R.
I is given by V over R at last. Okay. Then we will have
And then you will have um mm, okay, wait now. You will have 0.3 and 4, the voltage is 12, right?
yes.
Yeah, I'm not sure if I'm supposed to. I think you're gonna use 12 as your voltage, and then your resistance is gonna be I'm sus. Your resistance. Okay, but this is 1. So your resistance is gonna be, yeah.
So would the resistance be 12?
That is true, but you can write it as 6 plus 6.
No.
Sir, but that is taking me back to the answer I got at first, Mus.
Which is?
That's gonna be 1.
1, yes, 1 amperes. Yes, you possibly got to the answer, but you were not using the right principles.
I
So that was coincidental. So I'm saying that because let's say if one of the resistance is not six ohms, it's let's say 8 ohms, then you were gonna use guesswork and not get the answer. So the resistance that you use is the total resistance on this branch.
okay.
And given that you have the voltage across them, it means now you can get the value of I. Right? Which turned out to be 1 amperes, which makes sense because if the resistance is the same for both branches, the value of I will be the same. Because if I want to give an example, if there's 2 ways that people can go through to go out of a hall, and the 2 doors are of the same size, I feel like hypothetically we will have almost the same number of people going through those 2 doors because they're the same sizes. But if the other one was bigger, then more people were gonna flood into the bigger door. But here we have the same resistance, we have the same opposition. Okay. What is the current at A? Ronel.
So is it not just the current at 1 and 2 plus the current at 3 and 4, which is like 2?
Mamswan, do you agree?
Yes.
Okay. 1 plus 1, 2 amperes. 2 amperes. Okay. Okay. What is the resistance for resistor R? What is the resistance for resistor R?
But would it not be the resistance added together? So 12, no, 24 ohms.
3. Which resistors should I add?
So I added all of them, the 12 plus the 6 plus the 6.
Mamswan, do you agree?
Yes. Aren't the 2 connected in parallel, the 12 ohm and the other 12 ohm?
Yes.
So would we then not have to use but resistors in parallel to add them together?
I knew you won't agree. Rhonda, what do you remember this?
Yes, I remember it now.
Okay. Do you agree that you made a mistake?
Yes, sir.
Okay. So we're gonna have 1 over 12 plus 1 over 6 plus 6, which is 2 over 12, 2 over 12, 1 over 6. 1 over 6. Okay, so what is the value of R total? Mamswa.
The value of R total,
Yeah.
1/6. Didn't we just calculate R total?
Rona, what do you agree?
But I remember something about swapping them around.
You have to, because we are dealing with 1/RT, not RT.
Okay.
You are
Oh,
right.
okay.
Do you see?
Yeah. I see
So,
what you're talking
Mamson,
about.
what is the value of RT?
What is the value of
RT?
6/1? 6.
6 ohms. 6 ohms. Okay. Or RT across parallel is given by product over sum. And the product is 12 times 12 divided by 12 plus 12. What do you get? You can use your calculators.
You get 6.
Get 6. Okay, perfect. You can use either of the two formulas, 6 ohms. Okay. Now,
That's all we had to do.
yes, product over sum.
Then why is the question 5 marks?
No, we are not done. They
Oh,
want us to calculate the resistance of R. Yes. Yes. So how do we find the resistance of R?
So, Gandhi, what were we calculating?
Hmm?
What were we calculating?
Here we were calculating the resistance of the parallel connection.
Okay. So, why would we still have to calculate R if we've already calculated the total resistance? Like,
Then we must go down to our steps. The first step, we resolve the parallel resistance. And then the second step, must reconstruct your circuit. Now you have a new circuit. Let me reconstruct it here. We have a new circuit. It's 15 volts. And then you have R. Then you have, what was the effective resistance? It is 6 ohm. And that 6 ohm has 12 volts. And then here we have 2 amperes. Okay, now we have an unknown resistor there. How can we calculate the unknown resistance there at R? Mamswan.
so
Mm-hmm.
how will we calculate the resistance at R? Okay. I have total current.
Okay, total current. I feel like this step was unnecessary, but it's gonna be necessary somewhere. Okay, total current is given by
We already found total current, which is 2.
2,
Mm.
which is given by?
Which is given by
Voltage over R.
oh yes.
Ronald, do you agree with this formula?
Yes, sir.
Okay, so if we are focusing on resistor R, do we have the current that is flowing through resistor R? Mamswan.
If we are focusing on resistor R,
Yes. Do we know the current flowing through it?
no, not really.
Okay. Ronald, do you know the current flowing through it?
Hi, sir. No.
Okay, no problem. I think you will know. What? Okay. What is the current flowing through this point?
Flowing through which point?
Through this point.
According to our calculations, it's 1 ampere.
1 ampere was flowing through this
Oh,
branch.
no. It's 2.
And
sorry.
then we also have 1 ampere flowing through here. What
Yeah,
is
it's
the?
2.
It is 2. Okay, perfect. And what is the current flowing through there?
Okay, it's also 2.
It is also 2. Rodney, what do you agree?
Yes, sir.
Okay, so if you know the current that is flowing through the resistor R, and do you know the voltage across resistor R?
Yes, sir.
It is how much?
Is it not 15? 15 volts.
Mamswan, do you agree with 15?
The resistance that is flowing across resistor R,
The voltage
the voltage. Oh yes, no, it's 15.
is 15.
Yes.
Okay, so you guys are saying there was a total supply of 15 voltage supplied by the battery, and from that 15 volts, 15 volts went to resistor R, and then the rest went, and then 12 volts went to that 6 volts. That's what you guys are saying.
So, sir, do we then
Yes.
subtract 12 from 15?
I think you are going towards the right path.
Okay, so if we know that 12 volts was supplied to the 6 ohm resistor,
Yeah.
that means whatever's left is for the R, right?
Yes.
Which means that it was 3 volts.
Yeah, so let me write it in this way. Voltage at R is given by 15 minus 12, which is 3 volts. Rona, what do you agree?
Yes, sir.
Okay, so if you agree, I will take 3 volts and put it there. So this is equals to 3 over R. Okay, so we have 2 equals 3 over r. So how do we calculate the value of r? Oh, Ronel, are you lost with that too?
The what?
Did you see where the 2 come from?
Yes, sir. Yes, sir. Yes, sir.
Okay, so do you agree with that equation?
Yes, sir.
Okay, so now how do we calculate the value of r then?
So do you not just, okay, mathematics wise, do you not just take the 3 to the other side of the equal sign?
We
Oh,
can do
yeah.
that.
But yeah.
There's so many ways, cross multiplication, or you can multiply in whatever way. So r times 2 will give us 2r. 3 times 1 will give us 3. If we divide by 2, we will liberate r, and we will be left with r equals, I think it's 1.5. Ohms. Do you agree with that?
Yes.
You agree, right? I don't know why you agree.
Yes, sir.
Okay, let us use our logic now to see if our answer is reasonable or not. Okay, if the resistance of a resistor is high, the voltage supply will also be Mamswan, will it be high or will it be low?
If the
If the resistance is high, will the voltage supplied to the resistor be higher or lower?
it will be high.
It will be high. The higher the opposition, we have to send more power onto that resistor. So I'm trying to use logic, because the resistance that we got on R is actually 1.5. And the voltage that we got was, I think it was 3.
So that's 3.
It was 3. So logically, does this make sense?
Yes.
On a 1.5, we supplied 3. On a 6, we supplied 12. Does it make sense? It does. And if you divide the voltage by the resistor or the resistance, how much are you getting? Let's say if you are dealing with this resistor, if you divide 12 divided by 6, it will give you
2.
What is it?
It's 2.
It's 2, which is our current. If you divide 3 divided by 1.5, how much are you getting?
We're getting 2 as well.
Okay, now do you see that the current throughout the circuit, if you have a series connection, it remains constant? Do you see that?
Yes, sir.
Okay, so we are, do you guys have any question? Because the rest, I think we will finish it in the next segment.
No, I have no questions.
Romeo, any question?
No, sir.
Okay, so before I end this lesson, I just wanna say to you guys, whenever they put an unknown, let's say an unknown resistor or an internal resistance, usually they want you to apply the fundamentals of parallel connections. They want you to know that the voltage between point 1 and point 2 is the same as the voltage across 3 and 4. They will trick you, most of the times they will trick you with this kind of questions. So you must bear in mind. So if you get such questions, you must use what you have locally, because when you are dealing with Ohm's law, you have 3 parameters: voltage, resistance, and current. So if you have 2 of the Ohm's law parameters, it means you can get the other. And also, if you know that the voltage across 1 and 2 is the same as the voltage across 3 and 4, it means you can transfer the same voltage that you have calculated on one branch to the other. Then you will be able to calculate the other parameters. Are we all in the same page? Okay, so I will see you guys on Thursday. So we're going to be continuing with electricity. Then from there, we'll do more electricity problems, because I think electricity problems are the most, or can be the most difficult problems in the paper.
Yes.
Were they problematic in grade 10 also?
Yes, to a certain extent.
To a certain extent.
Yes.
Oh, okay, yeah. Because as an examiner, I mean, if I was an examiner, I think I think I would find a way to set a question which can only be solved by a few 2%.
So why would you want to do that?
so that you wake up and realize that you need to study more. If I was a teacher, I would do that. Yeah, but we're gonna do few more electricity problems. Then from there, I'm gonna slow down the pace, and then wait for what your teachers will be teaching, and then I'll try to catch up. But we're gonna do a lot of electricity problems.
Yes, sir.
Okay, I'll see you guys on Thursday.
Bye.
Cheers.